Zero Trust architecture is a cybersecurity framework based on the principle of never trust, always verify. It eliminates reliance on perimeter-based defenses by continuously authenticating and authorizing every user, device, and application before granting access, using context-aware policies and enforcing least privilege access.
ZTA assumes potential compromise utilizing micro-segmentation, real-time monitoring, and strong identity verification to prevent lateral movement.
Zero Trust is not a single product, but a framework of principles implemented through coordinated technologies and processes. It provides robust defense against evolving threats.
In this workshop, we will explore the key principles and show you how you can implement these architectures through a series of hands-on labs. We will show you practical examples covering everything from authentication and authentication, macro and micro-segmentation, quarantine and remediation, third-party firewall, and IPS integration, as well as monitoring, policy definition, and implementation.
Let's start by explaining the concept of a Zero Trust framework using micro-segmentation by contrasting the old approach of network security and the new one. The analogy for the old model is a fortress. We build a fortress around the enterprise. The fortress represents the firewall. And anything coming from the outside is untrusted and scrutinized, but anything from the inside is implicitly trusted and allowed. This trust boundary is both physical, as in what side of the wall you're in, and implicit, because as long as you're on the right side of the wall, no further checks are made. In this approach, we may have some basic segmentation in the form of VLANs, SSIDs, subnets, or interfaces tied to a firewall, but this segmentation is static and has more to do with network scalability and manageability than with security. This approach is obsolete for various reasons. The first reason is mobility. Users connect to other networks outside of the enterprise and can bring threats with them. Guests are not necessarily trustworthy. Not even employees are too blindly trusted. IoT devices have a higher risk because they may not be sanctioned and managed by IT. Their security capabilities are weak. But with this approach, if user or device is compromised, there's little to nothing stopping the threat from spilling over to other users and devices. Because once you are inside, you're free to move. Now, going back to the fortress analogy, if the only thing protecting the enterprise from the zombies outside is a wall, the day the zombies learn how to climb the wall, and they will, it will be carnage. Let's contrast this with a Zero Trust approach using micro-segmentation. In Zero Trust, users and devices are not trusted whether they're on-premise or off-premise. They go through the same checks. There's no such thing as trusting internal users. Every access is authenticated. If we talk about segmentation, the analogy would be that on top of the fortress that protects from outside threats, every house, every building has its own security to protect from other risks coming from the inside, such as criminals who live inside the fortress. But micro-segmentation, and software-defined micro-segmentation specifically, takes it another step further. On top of the fortress and the security around the building, we also have personal security guards that follow us around wherever we go. And wherever we go, we will be asked for our passport. This trust boundary is fuzzy, is distributed, and is mobile. It's not tied to a particular location, switch port, or VLAN. It depends on the identity, the device, the situation, the time of the day, etc. It's software-defined and it's adjusted on the fly. The necessity to this approach is that the components are managed and should be able to react and reconfigure as needed to respond to threats or change in the workflow. The concept of Zero Trust was coined by John Kinderberg from Forrester Research in 2010. 10 years later, in 2020, NIST released the architectural framework as Special Publication 800-207. This is a vendor-agnostic architectural framework, and you can download the latest version directly from the NIST website. As explained in this document, no matter what vendors might claim, no single vendor can provide the full Zero Trust solution. ALE is no exception. We don't provide the full solution, nor will we claim so. The first known implementation of Zero Trust principles is Beyond Corp. a proof-of-concept fictitious organization created by Google to illustrate the concept. Note that there's no Zero Trust certification, and whilst multiple organizations are at different stages of their Zero Trust journey, it's difficult to say that they fully adhere to these principles. To analyze the Zero Trust architecture, we will decompose it in data and control plane. Let's start with the data plane. The Zero Trust model, as defined by the NIST special publication, comprises a subject who's not necessarily a user, but let's assume that it is a user, who needs to access an enterprise resource. Access is granted by a policy decision point and a policy enforcement point. Note that both the user and the system that they're using are untrusted. Therefore, all requests for access must be assessed by a policy decision point. This includes authentication. They are who they say they are, and authorization. They have the right to access the resource from the system that they are using. Once this access is granted by the policy decision point, the policy enforcement point will enable it. And this is applicable not only for human users, but for all subjects, systems, and resource types. And this includes IoT, APIs, and application-to-application communication. Clearly, the policy enforcement point is a device in the data plane that must be traversed in order to gain access to the resource. There are different types of policy enforcement points. The most well-known example is a next-generation firewall, but the network itself can also act as a policy enforcement point by applying access control lists directly at the switch port or wireless access point. Enforcement can also be performed by way of agents installed on devices and directly at the application. All these have their own pros and cons, and we will likely need several or all of them depending on the specific use case. For example, a firewall is only effective for traffic traversing the firewall. ACLs can be difficult to maintain and limited in functionality and scale. Agents cannot be installed on IoT devices, and application layer enforcement tends to focus on users with limited awareness of the device or its security posture, etc. Moreover, any real-world organization will require a combination of different policy enforcement points to accommodate different locations and use cases. Let's now shift the focus to the policy decision point. The policy decision point is broken down into two subcomponents, the policy engine and the policy administrator. The policy engine makes the decision whilst the policy admin signals the policy enforcement point to start or shut down the session. To make its decision, the policy decision point must have access to multiple information sources that we see on the slide. Note that the policy decision point communicates with the policy enforcement point through a separate control plane. This could be an out-of-band management network or a logically isolated management network. NIST Special Publication 800-207 presents three approaches to a Zero Trust architecture. Enhanced identity governance is an identity-driven approach in which network access is not restricted. It is the access to resources which is restricted only to those with the appropriate privileges. From a network perspective, this approach is comparable to being on the internet, a hotel, or a coffee shop network. The network is not secure, and all security is added over the top at the application layer or with a VPN, etc. The downside of this approach is that it leaves the network open and susceptible to reconnaissance and denial of service attacks, but is the approach used by cloud-based applications precisely because they are running on the internet. In the micro-segmentation approach, the network is segmented by switches or firewalls that act as policy enforcement points, protecting small groups or individual resources and dynamically granting access to subjects. These segments are made progressively smaller, and ultimately each resource can be in its own segment. With software-defined perimeters, the policy admin element acts as an SDN controller which dynamically creates a communication path based on the decisions made by the policy engine. At ALE, we are a networking vendor focusing on on-prem solutions, and we will therefore focus on the micro-segmentation approach. This approach has some elements of software-defined approach in the sense that those segments are not static but dynamic and policy-based and follow the user or device as they move around. The National Cybersecurity Center of Excellence, through collaboration with the industry, has produced NIST Special Publication 1800-35. The goal of this document is to demonstrate several practical sample implementations of a Zero Trust architecture. This document presents 17 different implementations involving 24 different products. Each implementation involved at least a dozen different products to deliver the architecture that I showed 2 slides ago. In case you are wondering, in this workshop we will not create a full-blown Zero Trust architecture as described in this document, but we will focus on the aspects that most directly relate to the products that ALE offers, and that is the network itself. That is the goal of this workshop. To summarize, it's authenticating every connection and authorizing access according to the principle of least privilege. That is to say, granting the absolutely minimum level of privileges that are required to perform the task. We will make a distinction between device or machine authentication and user authentication. Indeed, permissions depend not only on the user but also the context, such as the device that the user is accessing the resource from and the security posture of that device. Our first lab will deal with machine authentication, user authentication, and least privilege. It's segmentation to prevent threat propagation through lateral movement and to reduce the blast radius in case of breach. As we will see later on, this is a combination of macro and micro-segmentation, and it's continuous monitoring and quarantine of any user or device that becomes non-compliant. We will put this to practice in a lab identifying an attacker and automatically moving the attacker to an isolated quarantine segment. Let's define those concepts of macro and micro-segmentation. There's 2 kinds of segmentation, macro and micro-segmentation. Let's illustrate it with an example. In macro-segmentation, the physical network is partitioned in different logical segments. These segments can be a VLAN, a combination of VLAN plus a VRF. It could also be a VPN when talking about shortest path bridging, MPLS, or even VXLAN or GRE tunnels. Any traffic between users or devices on different segments is controlled by a physical firewall. All enterprises use segmentation in some way, shape, or form, but not always for security reasons. Quite often, this kind of segmentation is used for scalability, administrative, or organizational reasons. If 2 devices are mapped to different VLANs, but they can communicate without going through a firewall, then they are on the same macro segment. A typical example of this kind of segmentation is running IP telephony on separate VLANs and VRFs, which are logically isolated from PCs. The next question is how to map users or devices to these segments. This can be done statically by switch port or SID, for example, but that's an obsolete way of doing things. It's too rigid and does not bode well with mobile users. On OmniSwitch and OmniAccess Stellar Wi-Fi, this segmentation is done dynamically. It's software-defined. When the user or device connects and authenticates, it is assigned a profile, and this profile will provision the user or device on the right segment regardless of the physical location, switch port, or SID. Up to this point, we are still talking about macro-segmentation, which does have security benefits, but in many cases is done for organizational or administrative reasons. For instance, cameras and door locks fall under the control of the access security group, whereas thermostats fall under the control of the building maintenance group. Micro-segmentation takes things one step further. Not all users are the same, and not all users have a legitimate need to access all resources. The same profile, which maps users to a segment, also includes a set of policies which add fine-grained control over user and device privileges, which are different for different roles such as HR or finance. This is known as role-based access, and this directly relates to the principle of least privilege. And so, even though cameras and door locks are both on the same segment, they do not need to use the same resources. The camera needs to communicate with the video recorder and the door lock with its server. There is no need for a camera to communicate with a door lock, just like there is no need for a door lock to communicate with another door lock. These fine-grained permissions are implemented through policies which are part of the profile and dynamically applied to the device after authentication. To summarize these 2 kinds of segmentation, communication between different segments is controlled by a physical firewall. This is macro-segmentation. But communication within the same segment is controlled by network admission control policies associated to the device or user role. This is micro-segmentation. One question that comes up is, do we really need both? Let's see what happens when you only have one of them. Let's start with macro-segmentation. The problem with this approach is that the firewall becomes a bottleneck. All VLANs have to be terminated at the firewall and we have performance issues. Or we start deploying more firewalls at the distribution layer. This is quite costly, but still not so good from performance point of view because firewalls are not wire rate. Lastly, there's now multiple policy enforcement points, multiple places to keep policies up to date. We need a tool to coordinate all that. Even with such a tool, if those policies are based on subnets and IP addresses rather than identity, it will be extremely cumbersome to manage. The other option is also problematic. If the only policy enforcement is done through network admission control policies, then this policy list will become very long and complex, and we may exhaust the device capacity limits. Bottom line, it's better to have a balance between these two forms of segmentation. Let the firewall control any traffic between different segments, and let the NAC policies control traffic within a given segment. By combining these two, we not only act on security threats that spill over from one security segment to another, but also the ones that move laterally across the same segment. To give a more tangible example, micro-segmentation is what stops an attacker who has managed to compromise a camera from using that camera as a pivot to compromise other resources such as a door lock. Now, if we look at the macro-segmentation technologies that we can choose from, there's multiple possibilities. Legacy means VLANs for layer 2 segmentation, which can be complemented with VRF for layer 3 segmentation. This is fine, but in a medium to large network, it may become too heavy as there's multiple touch points and configurations are required on every node and on every VRF. Service-oriented technologies such as SPB, MPLS, and EVPN decouple services from the underlay, and services, which here translate to segments, are configured only at the edge of the network as opposed to every intermediate node. Out of this, SPB is the simplest because it only requires a single control plane protocol. On top of that, it's fully integrated with the Access Guardian Network Admission Control Framework, which means that users and devices can be dynamically mapped to their segment on the basis of their identity or IoT fingerprint. This is the reason why in this workshop we will perform the labs with SPB. However, the concepts are equally applicable to EVPN or MPLS. Lastly, there's a few other technologies that can be used for specific use cases. L2GRE is the segmentation technology of choice to isolate wireless guest users from corporate users, and this is because this technology is directly supported by the wireless access point. IPsec or SSL VPN are also used when we require segments to be overlaid over a network, such as the internet, and encryption is required. We would typically use a firewall for that, and we won't be focusing on that in this workshop. Similarly, with micro-segmentation technologies, there's multiple to choose from. There's user-level profiles, there's private VLANs, there's client isolation on wireless access points, and port mapping on switches. In this workshop, we will focus on UMP because it's the most versatile one. It's also dynamic and fully integrated into the Access Guardian Network Admission Control Framework to achieve role-based access with network admission control policies, and for those products that support it, such as most wireless access points and the advanced or premium access switches, they can also include deep packet inspection application layer policies. And so by combining UMP with SPB, users or IoT devices can be seamlessly mapped to their macro and micro segment upon authentication or IoT fingerprinting, and they can receive role-specific security policies also. The last item is mentioned here for completeness and is the host firewall, such as IP tables in Linux or the Windows firewall on a Windows host. This kind of macro-segmentation happens directly at the OS level and not really at the network. Again, we mention it here for completeness, but we won't be covering that in this workshop. It's now time for our first lab, and in this first lab, we will do multiple things. We will explore authentication, and this is both machine authentication, that's authenticating the device that the user is logging in from, and then user authentication, authenticating the user on that machine. Even on the same device, different users can have different roles and different policies attached to those roles. That's role-based access. These policies will be applied at two levels. The micro-segmentation policies are implemented by means of user-level profile network admission control policies, whilst the macro-segmentation policies are applied at the firewall. The prerequisite for this is that the firewall needs to know the identity of the user to apply the right policies, and this means that we need to integrate our unified access solution with the firewall, so when traffic traverses the firewall, it knows which user it belongs to and applies the right policies to it. This is known as firewall single sign-on. As far as segmentation, we will use, as I indicated earlier, SPB for macro-segmentation and UMP for micro-segmentation. And here's the topology diagram. It represents an organization with multiple sites interconnected by an SPB network. Each site is a pod comprised of an OmniSwitch 6900. For those who know a little bit about SPB, this is a layer 3 VPN design. Each site is on a different subnet, but if you don't worry, SPB is not the focus of this workshop. At the central site, which is pod 1 in this case, we have a firewall and servers. The firewall is there for filtering traffic between different SPB VPNs and between those VPNs and the data center or the internet. We also have servers at the data center. To put this in zero trust terminology, there's two types of policy enforcement points: the switches, which apply network admission control policies, and the firewall, which applies firewall policies. Let's look in more detail at what we have at the data center. At the data center, we have an Active Directory server, which is dc1.lab.local. This server is also hosting Microsoft Network Policy Server and public key infrastructure services to issue certificates, as we will be using IPTLS certificate-based 802.1x authentication. So in this lab and throughout this workshop, the Network Policy Server will act as a policy decision point, whilst, as I mentioned, the policy enforcement points will be the network itself and the firewall. On top of this, we have OmniVista, which we use to manage the network and perform various configurations, and an additional server that we use to emulate the organization's intranet and that we use for testing purposes. With that, I leave it to you, Matthias. Let's look in more detail at what we have at the data center. At the data center, we have an Active Directory server, which is dc1.lab.local. This server is also hosting Microsoft Network Policy Server and public key infrastructure services to issue certificates, as we will be using IPTLS certificate-based 802.1x authentication. So in this lab and throughout the workshop, the Network Policy Server acts as the policy decision point, whilst, as I mentioned, the policy enforcement points will be the switches and access points, as well as the firewall. On top of this, we have OmniVista, which we use to manage the network and perform various configurations, and an additional server that we use to emulate the organization's intranet and that we use for testing purposes. With that, I leave you with Matthias, who will explain and demonstrate the lab setup, starting with machine and user authentication. So Matthias, over to you.
Thanks, Patricio. As mentioned earlier, we'll use 802.1x with IPTLS for both machine authentication and user authentication. Machine authentication. This is performed using a machine certificate, which maps the device to the machine auth profile. User authentication. This is performed using a user certificate, which maps the user to the employee profile. If authentication fails, the device or user is mapped to the restricted profile. In the next slides, I'll explain the access permissions associated with these profiles. Here is how the process works. When the laptop boots up, it automatically uses the pre-installed machine certificate to authenticate and gain access through the machine auth profile. Once the user logs into the laptop, it re-authenticates using the user certificate, granting additional access through the employee profile. Here are the policies we've implemented in OmniVista and pushed directly to the OmniSwitches. We have two policies, employee and restricted. Restricted policy. This policy only allows communication with the data center subnet. For instance, it enables Windows Server to push GPOs to renew machine certificates. All other communications are blocked. For example, if an unauthenticated user attempts to scan the local network, this will be blocked. A clear example of micro-segmentation. While communication to the full data center subnet is allowed, the firewall in the middle enables us to apply more precise rules. I'll demonstrate these firewall rules later. Employee policy. This policy grants broader access, allowing devices to communicate with each other for collaboration applications, such as file sharing or video conferencing. For demonstration purposes, we've enabled a basic rule allowing ping to showcase micro-segmentation. However, in a production environment, this rule might be more restrictive, permitting communication only on predefined ports necessary for collaboration between employee devices. Now, let's see how these policies are configured in OmniVista 2500s. Let's log in. We can go to Configuration, Policy View, Policies and Policy Lists, Policy Lists. Here we have the two policy lists, Employee and Restricted, explained earlier. Next, we can go to Unified Access, Unified Profile, Template, Access Role Profile. We can observe the three profiles mentioned earlier with their corresponding policy lists. These profiles' names should match with the filter ID sent by the network policy server, which we'll see later. If we navigate to Access Host Profile, we can see the default access role profile restricted, which is applied if the authentication fails. Now, let's move to the firewall web UI. We can go to the VDOM ZTN, which is the virtual instance we are using for this workshop. Then we can move to Policy and Objects, Firewall Policy. Here we have the three main rules for this first lab. The rule Pods to Data Center allows the 4 Omni switches to communicate freely with the servers so they can be managed by OmniVista, forward DHCP requests, and perform DNS queries. The rule Sites to Domain Controller allows all users to contact the DC1 Windows server to update their certificates via GPOs and perform DNS queries. Lastly, the rule Employee to Intranet allows only authenticated users in the employee profile to contact the intranet web server. This is achieved through integration with UPAM, which is configured to send radius accounting packets to the firewall, enabling it to identify which users are authenticated as employees. This means users in the machine auth and restricted profiles can only access the DC1 server, while users in the employee profile can also access the intranet web server. Here is the authentication process. First, the user authenticates using either their machine or user certificate via 802.1x. The OmniSwitch forwards this authentication request to OmniVista UPAM using the Radius protocol. In this setup, we use UPAM, the integrated Radius server within OmniVista, as a proxy. This configuration simplifies management by requiring only one manually configured network access device on the Radius server, UPAM. All Omni switches and Omni Access Stellar access points managed by OmniVista are automatically added as network access devices in UPAM. Since UPAM is acting as a proxy, it forwards the Radius packets to the actual Radius server, which is the network policy server integrated with the Active Directory on the DC1 Windows server. Based on the Active Directory database, the server determines whether to grant or deny access. Here is the Windows server. Let's navigate to the network policy server. And check the network policies. First, we have the machine auth policy. This policy sends the filter ID machine auth, which matches the access role profile we saw earlier. Next, we have the employee auth policy. This policy sends the filter ID employee, which matches the employee access role profile we also reviewed earlier. Now, let's try the authentication process. We will use user A in pod 4, who is not yet authenticated. If we check on the switch, we can see that the user is still in the machine auth profile. Let's log in. Now, if we check on the switch again, we can see that the user has moved to the employee profile. In the control panel, and network, under the properties of the Ethernet 0 interface, we can see that 802.1x is enabled. In additional settings, the option User or Computer Authentication is selected. In the computer certificates, we can find the machine auth certificate that was pushed via GPO. In the user certificates, we can find the employee certificate also pushed by GPO. Finally, let's verify access to the intranet web server. Great! The user has access. Let's hand it back to Patricio.
Thanks, Matthias. Now we will review some concepts that we alluded to in the lab, but it's important to develop in a bit more depth. These are some details about UMP policies, the differences between NAC and firewall policies, using allow versus deny policy list, and the concept of firewall single sign-on. So let's explore this in more depth. Let's start with user level profiles, and more specifically the NAC policies that are attached to them in a policy list. One thing to keep in mind is that these are stateless policies which are applied at packet ingress. Also, we tend to call these user level profile, but at some point we rename them universal level profiles because they can also be applied to servers, IoT devices, or even virtual machines. In this example, we have a client device communicating with a web server on TCP port 80. For the sake of simplicity, we will assume that both are connected to the same switch, but this explanation will be valid even if they were attached to different switches, and this is applicable in the VLAN as well as in the service domain, for example, with SPV. What we are highlighting here is that the client device is mapped to an employee UMP, and because these policies will be applied at ingress for traffic originating from the client device, then the policy will need to allow TCP port 80 as destination. That is, on top of other things such as ARP, DHCP, and DNS. But for the server UMP, the policy will need to allow TCP port 80 as the source because it is applied to traffic originating from the server. Of course, you can have a situation in which only one of the devices, either the client or the server, is mapped to a UMP. That means that the other device, at least at the access layer, has an implicit allow all, which is the default if you don't use ACLs. Network admission control policies are stateless, and this is a difference with firewall policies, which are stateful. And once the initial packet in a flow is allowed by a firewall, the firewall understands the session and allows packets flowing in the opposite direction pertaining to that session without having to create another rule. Let's analyze other differences between NAC or UMP policies and firewall policies. First, NAC policies filter on a 5-tuple, which is the protocol such as TCP, UDP, or ICMP, the source and destination address, and the source and destination port. That is to say that they go up to layer 4. The exception is deep packet inspection policies, which can go up to layer 7 if the access point or switch support them. A next-generation firewall, on the other hand, will go up to layer 7 and will add other things such as network address translation, and in the case of a unified threat management device, things like intrusion detection or prevention system, email security, network antivirus, and so on. UMP policies are bound to a device MAC address, whereas firewall rules are applied to interfaces or zones. NAC policies are done in hardware and at wire speed, but firewall policies are software with elements of hardware acceleration depending on the specific device, but usually not wire speed. NAC policies are static objects in the sense that things such as IP addresses are hard-coded, whereas in a firewall, policies can contain dynamic objects such as a host name instead of its IP address. This makes firewall policies easier to maintain. Lastly, switches have limited resources, specifically the TCAM or ternary content addressable memory, which is used for NAC policies, whereas firewalls have more resources and therefore can implement more and more complex policies. So in short, each have their strong and weak points, and that's why we use them both and combine them wisely to achieve what we need to achieve. Another point is that there's two ways of building policy lists, whether we are talking about ACLs or firewalls. An allow list is a restrictive policy that denies by default and only allows specific traffic. So it's a list of allow statements with a default deny at the end. This is what is required in the Zero Trust architecture. However, note that allow list can become very long when multiple different traffic flows need to be allowed. Deny lists do the opposite. They allow everything by default and only block specific traffic flows. It's a list of deny statements with a default allow at the end. This is not what the Zero Trust architecture requires. It does not adjust to zero-day vulnerabilities because the specific traffic flows that need to be blocked are not known upfront. This can also become very long as we discover more and more traffic flows that need to be blocked. The Zero Trust principles require using allow lists and specifically allowing only what is required and nothing more. However, from a practical standpoint, you may find that this is only possible with many policies that become complex, difficult to manage, and exceed the hardware capacity, or those policies have to be broad, which defeat the purpose. In reality, you may have to combine allow and deny statements to achieve the required outcome. The next point is firewall single sign-on. As we saw in the lab, users or devices authenticate to the network, whether wired or wireless. But if their traffic has to go through a firewall, how does the firewall know the user? Unless we integrate both, the firewall will only see traffic coming from a certain IP address which belongs in the corporate segment or zone, but it does not know the identity of the user or device that originated that traffic. That's why integration is required, and thanks to that, the firewall knows that IP address 10.10.10.10 is being used by Bob, who works in finance, and therefore it should apply policies according to that role. There's different ways of doing that integration, but most firewalls will integrate with Active Directory, and this is good for employees and other users with an Active Directory account. For other users or devices, specifically IoT devices that do not typically have an Active Directory account, we have to integrate in other ways. We can do this directly with UPAM, and on Spacewalkers, you will find application notes and tutorials that explain how to do that with major firewall vendors. It's now time for the second lab, in which Matthias will illustrate quarantine and remediation with third-party IDS integration. Let's imagine a scenario in which a malicious user launches an SSH brute force attack on a company resource. This attack may be detected by an intrusion detection or prevention system which is deployed in line with the resource, which is a server, and the IPS can block it. However, this malicious user could still try to attack other resources that don't require traversing the IPS, and the IPS would not be able to stop that on its own. This is where the quarantine manager function comes in. The IPS can alert OmniVista and inform of the attacker's IP address through a syslog message. OmniVista will look up the IP address in its database and determine that the attacker is connected to a certain switch or access point. It can then tell the switch or access point to apply a quarantine role to that device. In the quarantine role, the device is very restricted or completely blocked. It may only be allowed to communicate with or redirected to a remediation server. This is in case the device is not really a malicious user, but a legitimate user who got their device infected by malware, etc., and need to download some patches or operating system updates to clean up their device. The remediation part of Quarantine Manager allows users to do just that through a self-service process. Now, I leave you with Matthias, who will show you this in action.
First, let's check the configuration on the firewall. In the employee to intranet role, we can see that the SSH protocol is authorized. In a real production environment, you might not allow SSH access for every employee, but for this lab, we have authorized it. We have also applied an intrusion prevention rule to detect SSH brute force attacks. In log and reports, log settings, the firewall is configured to send its syslogs to OmniVista at the IP address 192.168.76.253. Now, let's go back to OmniVista. If we navigate to Security Quarantine Manager Rules, we can see the FortiGate SSH brute force rule. This rule is triggered if a received syslog contains attack equal to SSH connection brute force. And we use a regular expression to extract the IP address of the attacker. Next, let's try to launch a SSH brute force attack from user A in pod 4. I'll run a PowerShell script to attack the IP address of the intranet web server. This will take a few seconds. After a couple of retries, the firewall will detect the attack and will send a syslog to OmniVista. I'll cut this part so you don't have to wait. Let's check OmniVista's banned list. Oh, the user is now banned. In the reason field, we can see the log entry that contains the triggering expression SSH connection brute force and the attacker's source IP address. This IP is then used to block the client directly on the access switch. Finally, if we try to access the intranet web server again, we are redirected to a page that informs us we've been flagged for suspicious activity and need to contact an administrator to regain access. Great, this demonstrates that our integration is working as expected. Back to Patricio.
In this third and last lab, we will review a few tools that help in the design and planning phases of the Zero Trust migration and throughout. These are the asset inventory because it helps us get a view of the different types of devices that we have and that we will need to create things such as profiles and policies for. There's traffic monitoring, specifically deep packet inspection, which can go up to layer 7 and S-flow. Understanding traffic flows is key because security policies will need to allow or deny those flows. Lastly, we will see how to audit policies to verify that they are working as expected before we start enforcing those policies. This will prevent the disruptions that may result from enforcing incomplete or incorrect policies. One of the challenges of implementing a Zero Trust architecture is that most of the time, we will not be doing so in a greenfield fictitious organization like Google did with Beyond Corp. In a brownfield, the complexities stem from the need to preserve and leverage existing investments, integrating various and diverse technologies, taking stock of the organization's assets, and even defining what the policies are, all while at the same time minimizing disruption to the business as we do so. Different bodies propose different methods of adopting a Zero Trust architecture, and the one we see here on the slide is the one proposed by the National Cybersecurity Center of Excellence. What they have in common is that they are all multi-step and iterative processes because this transformation is not a one-day job. As proposed here, the first step is to discover and inventory the existing environment. You would know that OmniVista has some tools to help in this sense. Specifically, the IoT inventory allows you to create an inventory of your network devices that you can export to Excel for further processing. The second step is to formulate an access policy to support the mission and business use cases. Mission and business use cases are keywords here because if a device or a resource is not supporting a business use case, we should consider removing it because it increases the attack surface unnecessarily. We will then proceed to identify existing security capabilities and technology. What can we implement with what we have? And then eliminate gaps in zero trust policy and processes by applying a risk-based approach based on the value of data. That is to say that we will prioritize the most valuable resources in this iterative process. We will implement zero trust architecture components, people, process, and technology, and incrementally leverage deployed security solutions, and verify the implementation to support zero trust outcomes. I would personally add that we need to verify before we enforce, or else we risk disrupting those business processes. To do that, policies can be implemented in monitor mode, that is to say, that they log but not block, until they are fully validated, at which stage they can start enforcing. This zero trust architecture will continuously evolve and improve to keep up with the evolving threat landscape, mission, technology, and regulations. Another good read is the Zero Trust Maturity Model from the Cybersecurity and Infrastructure Security Agency, or CISA. This document analyzes zero trust architecture from the point of view of 5 key pillars: identity, devices, networks, applications, and data. On the network pillar, and specifically in micro-segmentation, it classifies organizations in 4 categories: traditional, initial, advanced, and optimal, according to the maturity of their micro-segmentation adoption. Without going into all the details, the traditional organization has little to no segmentation, uses large segments, and the configuration is manual. The optimal one implements distributed microperimeters with least privilege, and these configurations are dynamic, automated, based on risk profile, and evolve with application needs. What we can take away from this is that in a brownfield scenario in which we cannot start from scratch like Google did with Beyond Corp, because we have investments to preserve and a business which needs to keep running, the zero trust journey involves multiple steps over time and is an iterative process. Let's see some of the tools that can help in this transformation. First things first, we need an inventory report. We need to understand what we have and assess the business need. Any shadow IoT that cannot be justified should be eliminated, as it unnecessarily increases the attack surface. For the rest, we will need to secure them, and this includes creating authentication and security policies. The OmniVista IoT inventory can help with this. It can classify the different IoT devices into different categories and identify the manufacturer and even the model. This is done thanks to a combination of factors which include the MAC OUI, the first bytes of the MAC address, the combination of DHCP options, and the HTTP agent signature. The combination of these is known as the fingerprint because it allows pinpointing an IoT device amongst thousands of different types of devices. This IoT inventory can be exported as PDF or Excel, which we can use for further treatment, such as correlating with information coming from a CMDB or mapping the device owner or other relevant details. Note that we can also use the device category and map a role on the basis of that category. This is a first approximation to zero trust, but note that this is not as secure as authentication because these fingerprints can be spoofed. So we should aim for authentication, and more specifically EPTLS, using certificates, which is the gold standard in authentication and what we have used and shown in the lab. Once we have identified the types of users and devices that we have, we will need to plan the policies that need to be applied to them. On switches and access points which support DPI, we can use DPI to monitor application flows, and if we have configured authentication and roles for the IoT devices and users, we can break this down by UMP role. This is available when we configure the application enforcement option, not just the application monitoring. We can enable application enforcement and yet not enforce any application-based policy. Doing that, combined with user authentication and role-based access, will allow us to see these application monitoring statistics broken down by role. In this example, we see a medical imaging device and we see that it uses certain flows such as RDT, RTSP, and NTP. So we know that when we create security policies for this type of device, we will need to include these flows. If your devices do not support DPI, on switches we can still use S-Flow, but S-Flow is not as convenient because it cannot be broken down by role. It works at interface level, so any flow passing through that interface will be counted with no distinction between roles. However, you can still narrow down to the interfaces where you know that the devices of interest are connected. Lastly, S-Flow is up to layer 4 and not layer 7. Lastly, before you start enforcing policies, you should verify that they are working correctly. Here we see an example of QoS policy logs seen on a syslog server. While you are testing policies, in fact, what you can do is set the last statement to allow instead of deny. If you see that those counters are increasing, then you should investigate why. It may be that you did not include a policy to allow certain required flows. Note that you can set the login level such that you can see the traffic flows that match the allow all policy, and this will help you understand what you've missed. With that, I leave you with Matthias, who will take you through these labs.
Thanks, Patricio, for this detailed explanation. Let's see how this works in action with OmniVista 2500s. First, if we go to Network, IoT, Inventory, we can view our device inventory. For example, here we have a Wi-Fi client that failed to authenticate. This can help us identify a potential hacker's device. We also see Windows virtual machines, which are all our lab clients. However, in a production environment, as Patricio mentioned, you'll be able to identify all user devices, both corporate and BYOD, and differentiate them based on the UNP they are assigned to. This is incredibly useful for monitoring and creating appropriate policies. Next, we can go to Network Analytics Reports, where various reports are available using DPI and S-Flow. Let's check top applications. Thanks to S-Flow, we can monitor application usage. Here, since this is a workshop lab, the traffic is limited. But in a real production environment, this report will be invaluable for identifying the applications most used by your users, helping you prioritize and even block certain applications if needed. Then we can move back to reports and navigate to top-end applications advanced app bandwidth usage for all OmniSwitch 6860s and APs. Thanks to Deep Packet Inspection feature available on Stellar Access Points and OmniSwitch 6860, we can gather detailed information about application usage. In this lab, we can see only internal traffic since it has no internet access. We can also check the UNP access role profiles to view usage per user groups. Here, we only have profiles for employee and machine auth. However, in a production environment, we might see additional profiles for BYOD devices, contractors, or guests. And if we click on a UNP, we can see the applications used by this profile. For example, here we can check the usage for the employee profile. Lastly, we can monitor the policy list directly from the switch CLI. Let's check this on pod 2 using the command show active policy list. This is a great tool for creating and monitoring policies. As Patricio mentioned, it allows us to adapt them if necessary. I'll now hand it back to Patricio, who will conclude this workshop with some key takeaways.
That brings us to the end of this workshop, and we would like to close with key takeaways and some resources that can help you go further in your Zero Trust journey. A Zero Trust journey starts with network admission control, authentication, and authorization, implementing role-based access with least privilege. We continue with dynamic macro and micro-segmentation on the basis of the user identity. The macro segment is the network slice that the user or device is mapped to, whilst the micro segment are additional policies applied even within the same macro segment. Role-based access at the firewall will require the firewall to know the user identity, and this can be achieved by integrating at Active Directory or UPAM level. Quarantine and remediation allows isolating malicious users or compromised devices and remediating those devices if they're not malicious. The IoT asset inventory will give us a report of IoT device types that we'll need to plan to secure with authentication and security policies. The Application Flow Monitoring Application, or S-Flow, if not available, will help us understand the policies that we need to include within UMP roles. Before enforcing policies, we will monitor them in log mode until we are certain that they work correctly. And with that, we're on our way to a best-of-breed Zero Trust architecture. On spacewalkers.com, our technical community, we have multiple resources, some of which we highlight here. For example, we have an OmniVista UPAM architecture guide, integration guides for Palo Alto and Fortinet firewalls, integration guides for network administration control solutions such as Aruba ClearPass, Cisco ISE, and Forescout, network device hardening guidelines, and multi-factor authentication implementation application notes, so check them out. Several of these are also available in the form of a video tutorial which will guide you through the entire process step by step. Congratulations, you made it to the end of this Zero Trust workshop. Adopting a Zero Trust architecture is not a one-time implementation, but a continuous journey evolving in phases and iterations to meet the changing needs of your organization.
AED offers a streamlined approach to Zero Trust, leveraging dynamic micro-segmentations through user network profiles. This simple yet effective framework integrates seamlessly with any network technology, whether it is shortest path bridging, EVPN, or legacy systems, ensuring flexibility and adaptability.
Moreover, our solutions are designed to interoperate with a wide range of cybersecurity tools in your ecosystem. Through open standards, we ensure compatibility with firewalls, IDS, IPS, identity and access management systems, public key infrastructure, SIEM, threat intelligence platforms, and more, enabling you to build a robust and cohesive security strategy.
If you are ready to take the next step, our professional services team is here to provide expert guidance and support,
helping you successfully implement Zero Trust in your network. Thank you for your time, and we look forward to partnering with you on this critical journey.